Welcome to this video. We're going to study magnetic fields. This is an introduction to magnetic fields and their connection to electricity. Now take notes record what you see on the page in your notes. You don't need to get all the pictures down unless you'd really like to, but the most important thing is filling in those blanks from your notes handout. So first, the question we want to ask are, what are the different types of fields that exist in the world? Well, classical physics deals with physics before quantum mechanics, all that weird stuff comes along. In classical physics, there are three: gravitational fields, electric fields, and magnetic fields. Gravitational fields have the equation G equals F over m. That's how we find the strength G of the field. Electric fields have the equation E equals F over Q. It's the force per unit charge on a test charge. That's how we find the strength of the electric field. So you might expect an equation like that for magnetic fields too. But there isn't one. All we have is the variable B for magnetic field strength, or magnetic flux density as it's sometimes called. The unit for gravitational field strength is newtons per kilogram. Force is newtons, mass is kilograms, so there you go. What's the unit for electric field strength? It's newtons per coulomb. And because we don't have any special equation for magnetic field strength, we use capital T, the Tesla. This is a derived unit, but we're not going to learn where it is derived from. Write that down in your notes where you have the first blank. So where do these magnetic fields come from? There are two answers to this question. If you take a charge and you send it along on a path or cause it to move, then this moving charge produces a magnetic field. The same is true for wires that carry current. These charges are moving, so they produce a magnetic field. What does that field look like? We'll answer that question in a bit. The second place where magnetic fields come from is a bar magnet or any other permanent magnet. We call this a permanent magnet because this magnetic field disappears as soon as the charges stop moving. This magnetic field doesn't disappear in the same way. Now you might be wondering what makes a bar magnet so special. Why does it have a magnetic field, but your water bottle doesn't? The answer has to do with how the electrons are moving around the atoms. Because remember, you have electrons moving in atoms. And so because all of those electrons are sort of aligned, so to speak, in the way that they move, we actually produce a magnetic field at a larger scale. In your water bottle, the electrons are not aligned in the same way. This is a rough explanation. It's not entirely accurate, but it's a good way to think about it. At the atomic level, you have moving charges. So earlier we said there were three types of fields. Here's the information we had. Remember that gravitational field strength, this G value, is a vector, and it points where the test mass would be pulled. This electric field strength is a vector, and that points where a test charge would be pulled. So what about this? There is no equation. Where does the magnetic field point? It points where the north end of a compass would point. So let's take that example of bar magnets and examine the magnetic field. The best way to test is by putting a bar magnet around a bunch of compasses. So we're going to place this bar magnet inside. Right now the compasses are kind of random. And watch what happens when we put the bar magnet inside. The compasses are all going to turn. You can see them affecting the magnets. And when we slide one of these out and place the magnet inside, we can already see it affecting the compasses. Look at that. We get these loops. That's what the magnetic field looks like around a bar magnet. Here we are. This is pretty similar to the picture for a positive and negative charge. This is the electric field on the right. This is the magnetic field on the left. And we're making an analogy between the two. The electric field lines, we know, point from positive to negative. What about the magnetic field lines? They always point from north to south, so we can add some arrows to our picture. Go ahead and add those arrows. This makes sense because if you put a compass somewhere in the field, then the north of the compass is attracted to south of the magnet. So the field lines point from north to south. And you can see that if you follow a field line from north all the way over to south. But where is the field strongest in this case of the bar magnet? It's wherever the field is densest. The magnetic field is strongest near the poles because that's where the field lines are closest together. So put this into the notes as well. So what are the connections exactly between electricity and magnetism? There are two. And the first connection is one we've seen. If you take a charge, it produces an electric field. We already knew that. In fact, every single charge produces an electric field, even if it's not moving. But if you take the charge and make it move, then now, because it's moving, it produces a magnetic field as well. The same is true for wires that carry currents. Because these charges are moving, they produce a second field, a magnetic field. And that's our first connection. Charges in motion produce magnetic fields. We haven't shown you yet what those fields look like, by the way, but we're going to look at that soon. The second connection is one we have not yet seen. If you take a charge and you send it into an external magnetic field, so here's a field that we've set up, and we're setting it up with other equipment, well, once that charge is moving inside the external field, it feels a magnetic force. And that is our second connection. External magnetic fields exert magnetic forces on moving charges. This B field, this external field, is independent and separate from the field that the moving charge produces. We still haven't drawn this charge's own magnetic field. So there is a second field that we're not showing, which is produced because of connection number one. So we separate these two connections out. And now let's take a closer look at connection one. What does this magnetic field look like? Why haven't we drawn it yet in the picture? Here's connection one. If you send current to the left through this wire, you produce a magnetic field shown by the turquoise or teal rings. So the magnetic field around a moving charge kind of makes like a cylinder, or it looks maybe like a slinky. The field lines point this way, anti-clockwise if you're viewing it from over here. So that's it. That's the picture. Let's take another look. Here are two wires, and as the charges move, these rings represent the magnetic field. We can use a rule with our hand to figure out which way the magnetic field curls. So they just added arrows here. Let's take a closer look at that rule to figure out which way the magnetic field is pointing. The rule says stick your thumb with the current or with the moving charges, and then you curl your fingers around, and the direction your fingers curl in shows you the direction that the magnetic field lines are pointing in. So if your fingers curl around like this, if you follow my mouse, your fingers curl into the palm like this, then the field lines curl around in the same direction. Here's another picture from the side. If negative charge is flowing, you do the exact same thing, but instead of using your right hand, you use your left hand. Now we're going to skip to page 20 in our notes and explore just a little bit the second connection. It says moving charges get pulled on by external magnetic fields. There is a magnetic force that those charges feel. So imagine that we have two magnets. Here's the north pole of the first, here's the south pole of the second, and there will be some field lines pointing from north to south. A charge is moving up through this magnetic field. So, what's the direction of the magnetic force? You take your hand, you point your fingers with the field lines, because fingers look like magnetic field lines. You point your thumb in the direction of the velocity, and your palm, which is what you use to smack people, right? Your palm faces in the direction of the force. So the force is directed to the right. For positive charges, you use your right hand. For negative charges, you use your left hand. We can do the same thing with a wire. Perhaps there's a wire going up through this magnetic field, and you would also feel this rightward force on the wire. There's one very important thing to notice. Is this object going to turn? Will it start moving in a circle? This charge here? The answer is yes. Because the force is perpendicular to the velocity. So it's going to start to swing around and turn in a circle.